So this is the test review for our test on January something-ish, 21st, 22nd-ish, something like that. So I've already talked about the word, Clayton. You can ask about that later. So I don't want to get it on video. So what questions do you have, or what would you like me to do?
Can we go over the multiple choice?
Yes, I can do that. So if you'd like to look at that briefly. Interesting.
You got it on mine?
Yes, he did. So we can look at some of that. So Ryan, did you have questions about what? But it wasn't purple, was it, or was it purple?
It was purple. He also did it.
Ooh, okay. Well, then you don't need my black and white one, do you? Very nice. I appreciate it. What did you get for 9? I got D as well. What did you get for 12? I got B as well. What did you get for 10? I got D too. Okay. For 11, did you get D? I also did. Did you get C? I did too. What?
Great review.
Okay. Well, we can talk about the other things then. So, yeah. 20. Correct. 21, I got E. And 27, I think I talked about that. I think I got B for that. All right, so at least from your perspective, multiple choice, you handled pretty well. Were you able to do those timely, though? That's pretty good. Do other people have questions on this? Yeah.
You might kind of work through 12, just because, like, I don't know how moving the distance is
Okay. Okay. So this is a two-body torque problem. We do a couple of those in first-year physics. We did very minimal parts of that this year. So fortunately, again, it's one of those where you got to recognize it's a torque problem and then sort of conceptually work through that. So it says it's a horizontally uniform plane. And we don't know the length other than the fact it's a certain length. And it says that supported by ropes 1 and 2, points P and Q. So basically Q, P, the center is C, and then R. And it says that the tension rope 1 is 150 newtons. First of all, and then it's going to say, then this rope is moved to point R, which is halfway to the center, determine the tensions in each rope. Before we move that, before I move this rope, what would the tension in rope 2 be? Correct. So if I've got something on the all the way on the left and something all the way on the right, it should be proportional because it's a uniform rod. Like that. So at this point, any of the choices that don't total 300 newtons are off the table for A through E. So that basically gets rid of choice C and choice E. So if I'm moving this halfway out, or moving this here, do you think now it would have to pull up harder or not as hard compared to when it was out here? I think it will. And the reason is because if this thing is uniform, it says its center of mass is right there. So this thing is causing clockwise torque. Whatever is acting up over here is causing a counterclockwise torque. Those two things have to be balanced. So I thought of the pivot as right here in the middle. So when they were equidistant away from the middle, they had equal forces on them. So now if this is half the distance away, it should have twice the force on it compared to this one. So if I've got 300 total newtons, twice as many over here as over here, that's going to be 200 newtons, and that's going to be 100 newtons. And that would still maintain rotational equilibrium. questions either on those or other things you'd like to go over? Ian?
I'm currently going with the questions.
Yeah, that was a good electricity pun. Thanks.
So,
Your puns have a lot of potential. I know. You can't stop me. Resistance is futile. Do you have the capacitance for a lot more puns? No, not so much. Am I inducing a groan? Good. I'll stop. Those? Okay. So he's asking about one of the free response questions.
We did part C of the response question.
The NASA question? Okay. So part C. So this is actually, I think, tough because there's not a lot we've done with things that are not symmetrical orbits, right? And the other reason I think it's tough is because, well, I think it's pretty unfamiliar. So what this said is that if you inject something at the correct speed at a certain orbit, it would have a circular orbit. Now they're saying that they're either going to put it into that location, still tangential, but either going too fast or too slow. Okay. So we have something like this. Put this in here. And we're putting it in, let's say, that's point P, that's the center of Jupiter. We're putting it in too fast. Tell me something about it that's different than if we put it in at the correct speed. Yes, it's moving too fast. But other than that, what's causing its acceleration after the engines go off? Right. So I don't think that's going to change. I don't think the acceleration due to gravity would change if it's at the same location, if it's caused by the same planet. It would be a bit different. That's correct. So the angular motion would definitely be different. So in this particular case, I've got to think about, like, in my mind, if I'm going too fast, but I'm at the correct altitude, I've got the right amount of potential energy, but I've got too much kinetic energy. And so I've got to say too much energy right there. So overall, this thing isn't going to go in a circular orbit. So let's imagine that this thing is going way too fast. If this thing is going way too fast, what would it do instead of going in a nice circle? Yeah.
It'd be more like an oval.
It would. Where would it oval out? How do you think it would oval? It doesn't really matter, honestly. So I think the way that the solutions did it, showed it ovaling down like this. I could see you thinking about it like this. It doesn't particularly matter. So the idea is if it's got, that's a pretty bad oval. If it's got too much energy, it's going to swing out too wide. Like if you're going really, really fast, you actually can reach escape velocity, and you wouldn't orbit the planet at all. So an example of this is something like a comet that has like a really, really big orbital period and it's really elliptical. Tell me something out here about both its speed and energies compared to here. Yeah. No, you can pick on somebody else. That's fine.
Anyone want to be
You stay for the review.
Like,
What would have more potential energy?
It would. And compared to this spot, tell me something about its kinetic energy. Less kinetic energy here than here. So it's going to be going slower here, but it's further away. And so essentially the total energy here and here conserved, The angular momentum is also conserved. That's actually a really fundamental property, so it's going to be going slower out here than here. Angular momentum you can think of a couple ways. For a point source like a satellite, you can think of that as MVR. Is another way to think of momentum symbol is this. So basically you're going to be going slower, but you're at a bigger radius. Same amount of angular momentum here as here. So the idea is if you inject it too fast, at its closest point, at its point where you got this, it's going to be at the same orbit as it was before because that's where you placed it. But it's going to have too much energy, too much angular momentum, so it's going to swing out in a big ellipse. If you inject it too slow, at this particular point, it's still going to be the same location. If it's going too slow, its total energy would be too little, too low of energy. And therefore, instead of going in a nice circle, it would be an ellipse completely within what we had before. So it could be something like that. Okay. So the idea is here, if I look at that MVR, that mass is the same, lower velocity, same orbit initially. We're going to speed up at some points, but we're going to be like too close, and that would be conserved throughout the entire orbit also. So it's conceptually thinking about like, well, what the heck do you think would happen if you had something going too fast or too slow? Be an ellipse in both cases. It would meet that particular spot where it is injected every orbit again in both cases. But the purple example where it's going too fast, the closest location is where you injected it. In the brown location where you're going too slow, that would be its farthest location. Yeah.
So if you're going to drop it too fast, again, is it possible that it could leave? Like, because when I first drew it, I thought it meant like that was leaving.
Okay, so let me look and see at the specific question. So it says, describe the result of orbit qualitatively but specifically. That's great. So it says when the satellite is at the desired altitude over the equator, so that's that injection point P, its vector, velocity vector has correct direction, but the speed is slightly faster. So I'm betting that the slightly faster tells you that it wouldn't reach escape velocity. But yeah, if it just said faster, I think you could, if you showed it just going off the page, like you probably would want to briefly explain that. That's smooth, Wyatt. I like that. Oscillation is very relaxing. Good feng shui, I believe, is the correct term.
Feng shui, I don't believe so.
Feng shui or feng shui? Which is it?
Feng shui
Is it?
Colors, right?
What?
No, I got feng shui.
Yeah, it's like how things are organized so that they're
Oh,
appealing.
why is going in the house? But colors take into account. And furniture.
Other questions, either about responses, about the test, things you want to go over, multiple choices, doesn't matter. I'd like to help.
What kind of like overall like sections are on the test? It's been a while.
Okay, it has been a while. So multiple choices at the start. So there's 12 of those. 2 free responses. They're 15 points each. I'm trying to space it so like you can look and see like if they're on 2 pages, like one page would face the other, so you wouldn't have to flip pages back and forth for a free response.
Like what was in chapter 11?
Okay, chapter 11 dealt with some things with work and energy transfer. Chapter 12 was rotation, rotational inertia, torque. Chapter 12 was like everything 1 through 11, but compacted and done rotationally. Also had like rotational energies, things like that. Chapter 13 dealt with gravitation and orbits. And chapter 14 dealt with oscillations. They're fair game on the test. Everything for a semester is fair game, and we haven't covered it. I wouldn't give you like of 12 multiple choice questions, I'm not going to make 9 of them oscillations because it's not a huge part of the test, but it's something. Or could be something.
Is there going to be too much, like, basically with chapter 12, I know how we split it up, and like, they're doing stuff that I don't fully understand, like the torque line and stuff like that. Should that definitely be revisited?
So what I would say is this, like, there's a lot of things that could be asked about torque. Do you think you can solve them or figure them out? Do you have enough in your bag of tricks to do that without having to go back to something that didn't seem like it made sense to you? So like for me, I don't think about moment arms, and I don't think about that torque line. I do think about like I think about a little bit about the handle, but even that's not that critical. But I do think about like if something is in equilibrium, it's got to have like be in rotational equilibrium, which means balanced torques. And if it's not accelerating, it's got to be in translational equilibrium, which are balanced forces. So for something to be like motionless, it's got to have both. And a lot of the rotational problems you're thinking rotationally about. I think a lot of times when you have stuff like being pulled, like you've got pulleys or things pulling other things, you've got to think about torques, moment of inertia, angular acceleration. And then finally, like there's a couple people in some people in my first class of the day who are having a lot of trouble just converting back and forth between like angular and linear measurements. So I mean, on your formula sheet is this. The other conversions aren't there, but if you know that, you should be able to also say. You want to be able to go back and forth. So if I have a problem that's rotational, I try to see if I can think about it linearly, or at least think about the concept linearly, and then if I need to go into rotational mode, I'll do that. Because it's not as natural, for sure. Other questions? Yes.
Talk about the phase constant again.
Yeah, so that's going to have to do that. I can talk about it. You got to catch me if I screw up, okay? I'm going to go back and look because I don't deal with this often. But let's say we have, I'm going to go back to my formula sheet real quick. This A is basically an amplitude. So on your formula sheet it says X max, but that's what it is. If I asked you to do this, and this is like meters. So unfortunately it's like this is a rotational thing, and now you're having to get over here to meters. But if this is an amplitude, that would be in meters, times something angular-ish, would give us something in meters over here. So it's basically saying if you're oscillating back and forth at a certain angular frequency, a certain number of like radians per second, where would you be at any instant in time? If I wanted to think about something like this, this would be basically if I took the derivative of this would probably be not cosine of this plus the phase constant, what would it be? Negative sine. So it'd be like this. I'm going to come back to this in a minute because you're probably not liking the fact that that's like that. And if I want to find out this, and this would be negative cosine. So if you take the derivative of something in here, it's going to come up front. But the big idea is, whatever that is that comes up front here, this would be your Vmax. This would be your Amax. So your maximum acceleration, maximum velocity, maximum position. If we have something that's oscillating back and forth, well, if we have a cosine function at 0, are we at a maximum or are we at 0? Value. Maximum value. So this equation up here, if we're looking at position, we do something like that. So again, all this does is tell us like where we are, and then we can put a spot on the cycle. Where in this cycle? This is a position time graph. So x versus t. Where this happen? Where does the maximum acceleration happen? I'm going to go through time, and you're going to tell me. And I'm talking about magnitude of acceleration. I don't care positive or negative at this instant. Are you ready? And just say, now. And start. Okay, what?
Wait, are you talking about the next one?
Acceleration. Doesn't matter to me, but you just got to say it loud enough so I know what's going on. So ready and start. Okay, so here, here, and here. It's the second derivative of a position function. But basically, if I'm at that maximum location, I could actually go back to Hooke's law and think about this also. So if I know I've got a certain amount of stretch here, and I've got a certain amount of acceleration here, I can go back and figure out the force there as well. So sometimes, like, knowing these maximum values can be really helpful. Back to your original question, which was a phase constant, correct? So if I go back to something like this, say that this is now, most of the times I honestly think it's going to be 0 for things we would look at. But let's say this is pi over 2. What would that do to this graph? Like, where would it be at time 0? So at time 0, this is going to be 0. So I'm going to take the cosine of pi over 2, which is basically the cosine of 90 degrees. That would be at 0. So essentially, is that right? Is that right? I think it is. So basically, it's shifted to the left. I have a really tough time thinking about that. Like, is it shifted to the right or left? Because you think it should be shifted to the right. But essentially, it's like you're seeing something that's shifted time-wise a certain amount. So it helps me to think about if I see something like this, plugging in time 0 and thinking about where is that initial value. If I get that, I can move along. So it's just saying that it's kind of like with things we do linearly. If we start at a certain position, we use like x equals 1/2 at squared. That's a simple equation assuming our initial velocity is 0 and our initial position is 0. Well, what would happen if we ended up trying to solve for something that started like, was a projectile or something launched vertically that started like 30 meters above the ground? Where you are at each instant of time is going to be different. And that's basically what a phase constant does. And it's somewhat annoying. Let me know when you want me to make a prediction, Wyatt. Other questions, either about oscillations, rotation, earlier stuff, recommendations on pets. Do you have any pets? I don't have pets. I'm allergic to cats horribly. Dogs, not much. Most dogs, not much. If you brought your cat, is your cat friendly or not friendly?
She's scared.
She would come up and rub against my leg because anything that knows that I have horrible allergies, that's what cats do. That's what she would do. She would do that. It's just what they do.
You should get a moss ball.
What?
A moss ball. They're low maintenance.
Moss ball. Is that a pet? I would like a dog. If I'm not home enough, it's not fair to a dog if you're not home. Other questions? Yeah.
Will we be asked to find the phase constant like based off of the graph? Because I know that in one of the questions we had in like one of our chapter homeworks, it was something like that.
Yeah, so that's not going to happen tomorrow. Like, if you have something, I mean, I'll be honest with you and say that. You might have one question on a multiple choice AP exam that would be something like that. And basically what it would do would be it'll give you a graph, and it would say which equation corresponds with the graph, or something like that.
Okay.
And that's one where you kind of go through and check to see are there any that are obviously wrong, and if there's other ones that are possibly correct, you might want to take the time to do what I just did, which is kind of mentally look through it. I mean, you could also have those functions being sine as well as cosine correct. They'd start at a different space. The derivatives of those would be appropriate, shifted from that. Other questions? To go along with the pet theme, this summer I listened to a podcast that was nearly an hour long. And it was the theme of it was that the person thought that all pets should have names that end in vowels, so they just sound better for pets. So think about it. Like, what's the name? Do you have a pet?
Dog named Shiloh. Does that count?
That counts. That's a no. That's good. What?
Georgia.
But technically it ends in an H.
Oh, I don't know. That doesn't. That's a soft one. So maybe Lucky would be a good one. No, that is a silent. Stevie would be a good one.
Kennedy.
Well, that ends in a vowel. I don't know if we would use that as a pet name. Tater. Tate would. Ian, do you have a pet? How many pets? Cats or dogs or both? How many cats? How many dogs?
3 cats.
Oh, but you get a both over 2 cats in a household, you're becoming crazy. Okay. Other questions related to the test?
What's the answer to number 2?
I don't remember the question for number 2. So I'm going to say it's somewhere A through E, because that is the.
There's A through E in the test.
Yeah,
Are there Roman numeral questions?
I don't know. I might know. I'm not telling you. IV is what happens when you're in the hospital.
Mr. Force, you're still gonna do the thing like you get a 0%, you get a 200%.
We could, you know what? If
No,
I
no,
do
no.
enough tests this quarter, no, I can't do it this one, but like, if at the end of the quarter give a multiple choice test, I could do that.
You can do it on, yeah. Do it on this test, but don't tell Jake.
It's kind of hard to get a 0%.
It's very hard. Like, you really have to know your stuff.
You can miss a
very
free response. That's easy.
well. Right, yeah, this is a multiple choice test. When I gave it, I gave 25 multiple choice.
I know Tyler's always talking about that. I don't know if he actually successfully completed it.
He did not. I checked. He got
That
it
would
too.
be so
I
smart.
find it so easy to remember your answers.
What?
Like that one that we were doing.
Oh, yeah.
It can't be 300 words, so you like, take those answers